Hi everyone, my name is Anant. I'm a member of COPS, IIT BHU, our club of programmers, and today I'll be teaching you a little bit about bit masking and digit DP, right? So I'll try to do this video in parts so you can pause in the middle and take a break whenever you feel like it. And a simple thing to understand about bit masking and digit DP is that these are not algorithms, right? So if you are someone who is uneasy about learning a new algorithm, like you'll have to learn a lot, then you don't need to worry about this. They are just simple techniques, but they can be used in a lot of different questions. They are not very tough to understand, and a lot of questions are made on them, especially bit masking पे तो बहुत ही ज़्यादा. So I guess I'll start with bit masking first. Okay. So part one, bit masking. Suppose we're given an array like this one right here. So this array has three elements, 1, 2, and 3. And we are asked to perform some function f of x, and x here is every subset of this array, right? So we need every subset and we need to perform some function on it. That function could be anything from, it could be sum of all the elements, multiplication of all the elements, tell what is the maximum of all the elements. There's so many applications. There are easier ways to do these type of sum and multiply problems, but I'm just using that as an excuse to show you what bit masking can do, right? So with bit masking, what we're trying to find is, given an array of n elements, we need to find all the subsets that we can make from that array, right? So this array has, you will notice, three elements right here, and the number of subsets here is 8, and the relation is simple, that it's 2 to the power number of elements that are in the array. That gives us the number of subsets. It's simple PNC, like her element has the opportunity to either be in a set or not in a set, so it's two options, and simple PNC gives us 2 into 2 into 2 number of elements. It gives us 2 to the power n. In this case, it would be 8 subsets. So here are our subsets. Now, this part right here, it will be given to us in the question, right? So it's the given. But we need to find these ones. This is to find. Fine. These are all the subsets that can be drawn from 1, 2, 3. Now, there is an easy way to represent the given, right? How does Codeforces generally give you an array? It just tells you how many elements there will be, and then it gives you the number, all the elements that are in the array. So we need an efficient way to store this information as well, the one on the right? We need an efficient way to store all of this information as well, given all of this information, right? So how can we do it? Do it in a memory efficient way. Now think about it like this. Sometimes you're in Codeforces, you are given a question that is a geometric question, right? And you are given, say, 2 lines. Now, how will you store these 2 lines? These are mathematical functions. These are graph problems, but with in a computer, we can just store what is the slope and what is the constant, and through it we can store the entire line, right? Just 2 doubles and we can store the line. Similarly, we need to find a way to store all of these sets in an efficient way. So I'll just pick any random set here and we will try to store it. Like, say we picked this set. Okay, now I need a way to store this set in an efficient way. So how can I do that? This is my set right here, 1, 3, and this is the original array that the set is come from, 1, 2, 3. Now another way of saying a set जिसमें 1 और 3 है is a bit like saying कि एक set जिसमें 1 है as in yes, 2 नहीं है as in no, and 3 again is there, so yes. Or I can write, instead of yes and no, since we are computer scientists, we can write 1, 0 and 1, where 1 represents कि this has been included in the set, and 0 represents that it has not been included in the set, right? So we get this representation right here, 1, 0, 1, to represent this particular subset. Great. Now if you notice carefully, this is the, in binary, this is the representation of the number 5, because 5 is 2 to the power 0 plus 2 to the power plus 2 to the power 2. So in a way we can say that 5 represents this binary representation 101, and this binary representation 101 represents this subset. So we can also say that this subset is represented by 5 uniquely, like no other subset can be formed from the number 5, and 5 can represent no other number. So it's a direct relation between this subset and this number. So like if I just give you the number 5, right, you will be able to find what subset I mean, because you will take 5, you will write its binary representation, 1 0 1 यानी 3 आएगा, 2 नहीं आएगा, 1 वापस से आएगा, तो मेरा जो सबसेट बनेगा 1, 3 वाला बनेगा. So I have found this set and I have represented it as just the number 5. Similarly, we can do it with all these other sets. For all these sets, we can find what they mean in yes and no, convert it into 1 0 1, and then write the corresponding number. So take a moment here and pause if you want, and to get into your mind, set it into your mind that 5 can definitely be used to represent 1, 3. And if you've done that, you can see here how I have taken every single subset that we had written here, and I have converted them into no and yeses, or zeros and ones, and then I have written the number in decimal representation that those numbers represent. And these numbers are, as you can see, from 0 to 7, or the first 8 numbers, uh, or the first 8 numbers, or the first 2 to the power n numbers, where n is the number of elements in the array or the vector, of the set of whole numbers, right? So before, we didn't know how to get these in a memory efficient fashion. Now we kind of know how to get these, because we can just run a simple for loop from 0 to 7, and for every number, just like we did with 5 before, every number we convert it into binary, match it with the corresponding number in the array, and we can make a set out of it, right? So we'll be doing the same thing over here. We'll take every single number, we'll convert it into binary, and then we'll convert it into a set. I'll write a small program to show you guys how it's done, and then we can move on to more complex applications or some function that can be applied to all of these subsets. Okay. So suppose this is our given vector. It has 1, 2, 3, and we need to find every single subset. Like I discussed before, these numbers that can be used to represent the binary version, these are called masks, right? And because we are analyzing their bits, the whole thing is called bit masking. So we run a for loop. Now the upper limit of the mask was 7, because the number of elements was 3 and 2 to the power 3 is 8, so we go one less than that. So basically we go one less than the number of elements that are in the vector or the array, but let's define them first, right? So these are our masks, and now we will find every single bit of the mask. We know there are n bits of the masks, 3 bits, so we can just go bit to there. Is our output, right? So these are all the numbers. 0 represents none of the objects being selected, and 7 represents all of the objects being selected. We have right now converted into 1 and 0, but of course I can just put an if condition, right? And say if there is 1, then we include it into the set, and if there is 0, then we don't include it into the set, and apply that condition. So I'll write something along those lines now. Just take this. Equal to 1, right? So this means this element is included in the subset, else not included. Now say our function was that we need to perform on the entire subset was, say we need to find the sum, say. So int sum initialized at 0 for every mask, and if the number is included, then we just go sum plus equal to and for the mask, see, now this way When none of the elements were included, our sum was 0, and when all of the elements were included, our sum was 6. The same is true for all the corresponding masks. But this was too easy an example, right? If I took 6 here and 10 here, or 9 here, then also it applies because selection is happening the same way, right? So for all possible subsets of this array, just by a few lines of codes or 2 for loops, we are able to find every single possible sum. Now, you might be wondering what is the time complexity of this? Because there are 2 for loops, we can calculate it very easily. The first for loop runs for 2 to the power n iterations, and the second one runs for n bits. So n. So the total complexity would be 2 to the power n multiplied by n, which is quite a lot. So uh, if the constraints on a particular question in Codeforces are very small, then you can think about bit masking. If they are not, then you can't really think about it. So now we'll move on to DP with bit masking. So if you've done dynamic programming before, this will be much easier, but I'll just run through it again. Dynamic programming usually involves calculating the answer for various states. We are usually trying to get the answer for the final state, but to do so, we need to find the answer for the middle states, and the answers for the middle states contribute towards the answer for the final stage, right? Well, we're doing a similar sort of thing with DP with bit masking, except instead of numbers this time, we're going to have sets. It's going to be a set, this is going to be a set. The final answer will be an answer for the set, but the answer for this set, say, will have contributions from these two sets, something like that. Now, previously we would have found it difficult to do so because we didn't know how to represent these subsets, but as we have talked before, now we can represent subsets with simple numbers. So doing dynamic programming with different subsets such that the answer for one subset is contributed by answers from another subsets sounds difficult, but it is simply just like regular dynamic programming. So I picked an example that has a short statement. This is a really short statement. I don't think I've ever seen a statement this short. But basically the question says that you're given a graph and you're given all the edges that are in the graph, and you have to find the number of simple cycles in it. Simple cycle is a cycle where a vertex does not repeat itself, right? Now this sounds simple, but notice how the constraint for the number of vertices that are in the graph is just 19. This is a hint sort of given to you that something like bit masking might be applicable here, because like we discussed before, the time complexity for bit masking goes up to 2 to the power n, sometimes in that, even that into n square, something like that. So when n is 19, it is very much doable because 2 to the power 19 is very much in the range for the time 1 second or 2 seconds. So how do we find the number of simple cycles? You can go and read the question, by the way. It's contest 11 problem D, and I recommend you to go and read the question, read the constraints, and once you have understood that, you can come back here and let's start discussing the answer for it. So say these are all the vertices that have been given to us, and we need to find the number of simple cycles. So I'll just draw a few simple cycles. This could be a simple cycle, right? Take another color and say this could be a single cycle. And let's number the vertices a little bit. 1, 2, 3, 4, 5. So one cycle is 1, 3, 5. The another cycle is 1, 2, 4, and 5. Now, until now we had been representing the bit masks and using them to represent a set. Now I will use them to represent a set that is forming the cycle, right? So say my bits are 0th bit, first bit, second bit, third bit, fourth, fifth bit, and on and on and on. And all of these bits represent the vertex. So for this cycle, the green cycle, I can say that 0, 1, 0, 1, 0, 1 is the mask that represents this cycle. and I will associate the count of all the cycles that are like this, that include 1, 3, and 5, and no other vertices in, and represent this and attach it with this the following mask. And similarly for orange, I can mark 1 and 2 and 4 and 5. So the states of the DP can be represented by this mask, and the mask in itself is a number, right? So I can just make a DP of the mask, and that can store for us all the number of cycles that are made from edges, made from vertices who are set high in the binary representation of that mask. So we'll make a little change here. Remember how I said that DP of masks, we could DP of mask, and here the cycle will have the mask 1 1 1 1 1 because all the 5 elements are involved. We will store it in DP of mask, but the problem is that if we store the number of full cycles in the DP, then we will not be able to make transitions from one state to another, because बड़ी वाली cycle छोटी वाली cycle से नहीं बनती ना. So what we're looking for is not actually cycles. What we're looking for is actually arcs. So for example, if someone told me there was an arc that goes from 0 and ends up at 4, and there was one arc like this, then, and they also gave me another piece of information that was there exists an edge between 0 and 4, then can I not tell you how many simple cycles are there? Because I can say that, oh, there is one simple cycle, there is a arc that goes from 0 to 4 and there is an edge, so when you connect the arc with the edge, you will get a simple cycle, right? So in the DP of mask, if all the bits are activated, that signifies, in our case, in this case, that there is an arc that involves all of these points. Now, to make sure that this big cycle, that the green one, is not counted multiple times, we will make sure that we not only tell what is the mask, which represents what all the points are involved, we will also tell you what is the starting point and the ending point, right? So say we'll make this DP a two-dimensional DP, and we'll put an ending point here. In this case, the ending point would be 4. And we also want to know starting point. I could put another one here, or I can just say that the very first bit that has been set in this mask can function as my the very first bit in the mask can function as my starting point of the arc. And in the end, when I have gotten all the DPs, when I have calculated all of them, for every pair of mask and ending point, I will see if the first bit of mask has an edge that goes from the F to EP, and if there is, I will add this to the answer of the number of simple cycles. This will make sure that my simple cycles are not counted multiple times. At max, they will be counted twice. Now let's talk a little bit about transitions, right? Say we need to find whether or not there exists a arc such that the purple one, right? So that it goes from 0, 1, 2, 3, 4. So it starts at 0, it ends at 4, and it involves the numbers 1, 2, 3. We don't need to know in what order 1, 2, 3 are, because if we make a transition further from this, we only need to know what is the ending point. And in order to check whether or not this forms a cycle at the very end, we only need to check what is the starting point and what is the ending point of the arc. So the middle points do not matter in which order they come, but of course the first point and the last point matters. We will represent the first point as the second dimension of the DP. We will represent the last point as the second dimension of the DP, and we will represent the starting point as the first bit that has been set in the mask. We already discussed that bit. So if you look at this carefully, if I tell you that there already exists an orange arc that goes from 0 and it ends at 3, and I tell you that there is an edge in the graph that goes from 3 to 4, can you not combine these two facts to tell me that yes, there is also an arc exists that goes from 0 and that ends at 4? What I'm trying to say is that the DP such that all the numbers are involved, so 0, 1, 2, 3, 4 are involved, that ends at 4 exists if the DP where 0 is involved, 1 is involved, 2 is involved, 3 is involved, but 4 is not involved, and this arc ends at 3, right? This is the orange arc, this one is the orange arc, and this one is the purple arc, right? this purple arc exists if orange arc exists, and I can say that there exists an edge that starts from 3 and simple enough. Similarly, say there was, I'll take one more case to really drive the point home. Another arc between, suppose we need to find another arc, right, between 0 and 4. It starts at 0, it ends at 4, and it includes all of the numbers 0, 1, 2, 3, 4. But this one goes something like this: 0, 3, then 2, then 1. Okay? And we know that there exists an edge. We know there exists an edge between 1 and 4. So can I not say again that yes, there is an arc that goes from 0 to 4? It may be a little difficult to see because it crisscrosses, but obviously these points are not exactly in a plane. So in this case, we can say that yes, again, in the case of DP where all the numbers are involved and the arc ends at 4, it begins at 0 because it's the first set bit. This we can add to it the DP where all the numbers are involved except 4, and this one ended at 1, the red arc. So purple, you can also add to the count of purple all the cases of the arcs where all the numbers are involved such that it ends at 4, the case of where almost all of the numbers were involved and it ended at 1. So it started at 0 and it ended at 1. And for this to happen, there must also be the condition that there should be an edge between the number where it ended 1 and the number where we're trying to end it 4. Now from this example, we will try and find a more generalized equation for transition. We can basically say that dp of a mask such that it ends in some random number I, and of course ith bit should be set in the mask, and ith bit cannot be the least significant bit that is set high in mask because वहां से तो हमारा arc शुरू हो रहा है and I पे हमारा arc खत्म हो रहा है. So mask and I can be dp of mask such mask dash such that mask dash में जो mask में जो ith bit set था उसको ऑफ कर दो, right? And ith bit ऑफ करने के अलावा it ends on a number j. So this new part on the right is all the number of arcs that begin from the again the least significant bit. जैसे इसमें 0 से start हो रहा था और 4 तक जाना था, तो उसके mask के लिए we found another mask that begins with 0 and ends at either 1 या फिर ends at 2 या फिर ends at 3 such that वो बाकी सबसे घूम फिर के जाए. मतलब it in the path already involves 0, 1, 2 and 3, but उसी order में ना हो, किसी भी order में हो, at least as long as it begins with 0 and it ends at j. J here can be 1, 2 या फिर 3. I is 4 and the mask is here in this case would be 1, 1, 1, 1, 1, and mask dash is the same mask, but this time the ith bit where the 4 was set before is not set right now. And this will be the right part will contribute to the answer of the left part as long as there exists an edge between j and I, right? So as long as there was an edge between 3 and 4, the arc that went from 0, 1, 2, 3 will contribute to an arc that goes from 0, 1, 2, 3, 4. So now that we found our transition, basically it's a question of just writing the code and we'll be done. So you can skip this part if you want to do the question yourself, but I'll be solving the question anyways. So let's just, so the constraints are for the number of vertices 19, then we'll be given the number of edges. And so I've just taken the vertices and edges in and I've made an adjacency matrix for it. I didn't make an adjacency list, I felt there was no point. The number of vertices is already so less, so what does it matter? So let's just write the code for our DP. Mask can go from 1 2. You don't need to solve for mask equals to 0 because there will be no arcs that involve 0 number of vertices, right? So for every mask, we can calculate two integers. One will store the count of how many bits are set high in the mask, and another can store key whatever the arc the mask is representing, what is the starting point. Like we discussed, the starting point would be the first bit that is set high in the mask. So I can use a C++ function provided by a compiler actually. It automatically calculates how many bits are set high in the number, and it will give it to the count, and let's just call it start, the other number. So to set start, we'll go Mhm. Pick. So after this, we have set both our variables. We've got the count, we have got the start. So all we need now is the endpoint of the arc, the new endpoint, I guess. Can be any of these. But it can only be an endpoint if it is actually set high in the uh, arc, right? So first of all, we'll take care of a very base case. If the count is 1 and end equals to start. Count equals to 1 and end equals to start, we're talking about an arc that is like one vertex long. It only involves one vertex and the starting point and ending point is the same. So of course that will exist now. So we can just go ask equals to 1. In all other conditions, we will also have to make sure that the number of vertices is now more than 1 and mask bit that the end signifies is actually on. And we need to make sure that end is not equal to start, because otherwise arc की जगह circle बना देंगे हम, right? And we don't want to make circles, we only want to make arcs. So we can do now for end previous endpoint was from this endpoint. If there exists an edge from the previous endpoint to the new endpoint, then of course there will be a new arc. Mask that ends at the new endpoint plus equal to TP of mask, and I'll be removing that one bit, that the endpoint bit, right? So just go like this. That ended on the previous endpoint. Yeah, that seems correct. Just make sure I don't know, make mistake or not. For every mask and for every endpoint, I'll have to see if it contributes to the answer or not. And to do that, I need to make sure that अगर circle है, then count should be more than equal to 3, obviously, because उससे छोटे circles तो होते नहीं. It needs at least 3 vertices to form a cycle. And the other thing would be make sure that there actually is an edge between starting and the ending point. Yeah, that seems correct. It's an initialize. And we should make all the ints long just in case I don't want to have memory overflow. This way I think all the arcs will get counted twice, right? Because 1 से 4 वाला arc था, but 4 से 1 वाला भी तो होगा, that will get counted as well. So I think I need to divide the answer by 2 here. And I think I've taken care of all the conditions. Let's just check anyway. 7 was the answer, right? 7. Oh, I hope this is correct. It's fine. If it's not, we'll just debug, I guess. Yes. Great. So just in summary, I would say that if you didn't understand the last example, I mean, it's fine because you need a lot of information about DP and how graphs work to understand it. But what I would want you to take away from this is that at least all the sets, all the different combinations, whatever they may be represented, can be just be represented by simple numbers. 5 was able to represent 1 comma 3, and like that. If any number can be used to represent an entire set, and its bits can be used to represent whether or not that particular element is included in the set or not, then basically I have stored all this information that usually would have taken a lot of memory into just the number of masks there are. So this is a very practice heavy sort of topic. Like I said before, it's not really an algorithm. It's the answer we wrote for the last question was completely dependent on what the question was, right? For if you encounter different question of DP with bit masking, it will be done in a completely different manner. So what you need is practice on this and to know that you are able to represent all the sets as different masks. So we can talk about digit DP as well. It's a different technique, completely different from bit masking. It is not related at all. So if you didn't want to do bit masking, you can just do digit DP on its own as well. The questions for digit DP are usually put something like this. They are like for a range A to B and all the numbers in between. We have to count all the numbers that satisfy a particular property X. Now this property X can vary, right? It can be like count all the numbers that when divided by 5 give me 3, right? It can be a property like that. Or they can say that count all the numbers that have the digit 6 in them 5 times. Have the digit 6 in them 5 times. Something like that. So they can vary a lot. But the main approach to solving problems like digit DP is to first of all convert this problem into a problem of single parameters. What we will do is we will find the count of all the numbers from 0 to B, and we will count all the numbers from 0 to less than A, or you can say less than equal to A minus 1. And then we'll get some 1, some 2, and then we will subtract them to get the count of the numbers between range A to B. What this has done is it has converted our function from taking A and B two parameters to just taking one parameter. So you can define a function f that will take a parameter. In one case it will take the parameter B, in another case it will take the parameter A minus 1, and it will output the count of the numbers satisfying the property X that goes from 0 to that number. So it will take in a number n and it will return the count from 0 up to n. Okay. Just as a simple example, I'm going to ignore the property X for now, and we're just going to find the number of count of the numbers from A to B. Of course, the answer is going to be B minus A plus 1, right? But I will try to find the count of all the numbers from 0 to B, try to find all the count of the numbers from 0 to A using digit DP. And if you can see how we apply the conditions here, you will be able to see how we apply the conditions in other cases, right? So we will first find count of all the numbers from 0 to B, then you find count of all the numbers from 0 to A and subtract. So let's just make a function f of x that returns count of all the numbers from 0 to x, probably returns x plus 1, right? So how do we do that? So let's say our job is to find the numbers less than 6666666, just a random number I've taken, right? So if there is a number that is less than 66666, then you can say that it will have 6 digits or less, right? So it can have 6 boxes here. So these 6 boxes represent the 6 digits it is going to have, right? And what is going to happen is whatever digit I put in one box will directly tell me what digit I can put in the next box. Based on this, I have to tell what I can put inside this box. And as such, it becomes sort of like a DP, because as we discussed during the bitmasking video as well, DP is when another state is influenced directly by a state that was before it. So let's start. How many digits can we put here? Can we put 9 here? Like obviously not, because whatever if we put 9 here, doesn't matter what we put after this, the number will become 900,000 something something, and that is obviously bigger than 66666. So saying 66666 a lot. So we won't be putting 9 here. We won't be putting 8 or 7 here. We can put 6 though, right? We can put 6 here. We can put 5, or we can put actually anything from 0 to 5 here as well. So there's a reason, by the way, why I'm separating these two cases where we put 5 and where we put 6. Because once we have put 5 here, I think we can all agree it doesn't matter what digits I put in the rest of the number. Even if I were to put the maximum like 9, 9, 9, 9 for all of them, even then it is less than 666, 666, because it doesn't matter. Once we have input here in any digit, ith digit, if we have input a digit that is less than the corresponding digit in this number, then we can be sure that no matter what number we put after that, it will always be less than this number. But the problem comes in the case that where we have put 6. So in all the cases that were not 6, I can say that of course we can put 10 digits here of any kind from 0 to 9. We can put 10 options here and like that. So 10 into 10 into 10 into 10 into 10, 10 to the power 5, which is uh, double zero. This is how many numbers multiplied by all the options. So 0, 1, 2, 3, 4, 5. That's 6 options. So at least we have 600,000 numbers that are less than this given number x. I'm just going to call it x from now on. Okay. Now that we have decided that, now to find the rest of the numbers. So what number can I put right here after 6? Look, I can't put any other number that is more than 6 here, because if I put 6, 7, then doesn't matter what I put afterward, it is going to be bigger than this number, right? So again, we have the similar case that we had in the first column, where in the second column I can either put 6 here or put anything from 5 to 0. If I put anything from 5 to 0, again in the next 4 columns it doesn't matter what I put in. So 10 options for all of them. So it will become 10 to the power 4 multiplied by 6. So our answer we had previously calculated was 600,000. Now we have 66,000 numbers at least that are bigger than 666. And if we put 6 here, then again the same thing happens. Now what do we put here? We either put 6 or less than 6. And if we put 6 here, then again the condition will follow. So as long as we are putting digits here that are exactly following this same pattern, 666, 666, till then we are not sure about what to put afterwards. We have to apply some constraints afterwards. But as soon as we put one digit, once if I put 4 here, and then 6, 6, 4, if I put something like that here, then I can be damn sure whatever I put afterwards, it doesn't matter, it will always be less than this given number. So as long as we are exactly following the number that was given, we have to manage some constraints. We don't know what to put next. We have to check whether or not we can put in. But as soon as we put one digit that is less, after that we can put any digit from 0 to 9. So that's 10 options. Similarly, like this, we will follow for all the steps, and ultimately, of course, we will get the answer that 6666 6. That's how many numbers there are between 0 and this number. So we'll be going for a slightly more difficult example before directly heading for questions, because there's not a lot of theory here. So now our problem is we need to find numbers that are less than this given number that have 5 in them. Remember we talked before about properties, and so this is our property x that all the numbers have to satisfy, and this is our number that is a given number n, let's say. Now maybe you remember from the last example, as we were filling this, whatever happened in the next digit was directly influenced by what had happened before. So if we're going to solve this, the kind of DP we're going to need is going to be like 3-dimensional. Why three-dimensional? Because we need three parameters that need to be controlled. If we have solved for the first I digits, then we need to know how many digits we have solved for, so that's I. Then we need another parameter j, which is like 0 or 1, which will tell us whether the number we have filled so far is definitely less than n or not. If we had filled like 1, 2 and then 1, as soon as I filled this third one here, then that would mean that this number would, doesn't matter what we fill afterwards, this number will definitely be less than n. So at that point we will turn j to 0. But if the number is 1, 2, 3 and the last three numbers I haven't filled yet, then there is a possibility that this number could still become more than n depending on what digit I fill afterwards. So we are not sure. If I write 1, 2, 3 blank blank blank, then I don't know whether this number is going to be more than 1, 2, 3, 4, 5, 6, or is it going to be definitely less. So if I can't say for sure, then I'm going to use the other value of j. So j can have two values, 0 or 1. So the last parameter we will need, t, that we didn't need before in the last example, but we only need in this example, is because of the property that if the number already has 5 in it or whether the number doesn't have 5 in it. So that is great, and it is also going to have only two options, 0 or 1, depending on whether the numbers we have calculated so far have 5 in them or not. So this is going to give us the count after processing I digits. The next line. This dp of I comma j comma k will store the count after processing I digits, j telling us whether or not the number we have made so far is less than n or not, and k telling us whether the numbers have 5 in them or not. So since j and k can only take 2 and 2 values, if the number of digits is like n, then the total memory complexity becomes n into 2 into 2, which is 4n, which is fine. So now we move on to the transitions about how we will go about filling this dp up, right? So as we talked before, the second and third parameter of the dp signify whether or not we have been following the pattern that was given in n and whether or not the property p has been satisfied. So these are all the dp transitions that I've just quickly written down. You can see for yourself, try to find out what they actually mean and how are they contributing to the sum this time. These are all on the right hand side, these are all I minus 1, and the left one is we are making the transition to the next digit basically. But not all of these conditions will be added. Like for example, I have marked a couple here with hashes. I'll change the color. I have marked a couple here with hashes, and these will only happen if the digit we are now adding, z, is not equal to 5. And the ones that I've marked with the @ sign, these two conditions, they will only be added to these when the number we have added is 5. Right? Similarly, with all these other conditions that I haven't marked, not all of them will always happen. We'll have to put if and else all over our code, but eventually you will see that in broad terms these are our dp transitions. So if you have any experience with dynamic programming, you will be able to write these transitions. And what we're basically trying to do is maintain here two parameters other than just how many digits we have processed. The two parameters we're trying to maintain is whether or not we have followed the pattern and whether or not the property has been satisfied. Depending on the property, depending on the number given, you will have to write, you will see how different types of DP will contribute to the next stage. So a good question to start with for digit DP would be this one. It's contest 628's problem D. You can go look it up. It's not very difficult genuinely, and honestly, I would want you to do it yourself because unlike the last question that I solved for bitmasking with DP, which is a very tough topic, it required a lot of prerequisites and it required a lot of explanation. You couldn't just do it on your own. But this one you can definitely do on your own. Questions like this come in Codechef all the time. I think it was a similar question was in long challenge as well recently. So if you have read the question, I suggest you try to attempt this one yourself, and you can pause the video right here. After that, you can come back and I will explain to you what I had written in my code and you can match. Okay. So one important thing to note about this question was you can't just do function of b minus function of a minus 1, because to calculate a minus 1 would be kind of a hectic thing. A was a number with 2000 digits. So what you need to do was calculate for b, calculate for a, subtract it, and separately calculate whether a followed that condition or not as well, and add that to the final answer. So there is a function simply for calculating whether or not that one particular number a satisfied our question or not. Now, a very rudimentary solution would have been to just put every number from a to b inside this function, which calculates whether or not it satisfies the condition given in the question, and solve for that. But it would have taken too much time, right? So we did our DP. What we created here was again a three-dimensional DP, just like the example I was talking about before. The three-dimensional DP is created here as well. Here the first one again signifies how many digits we have processed. The second one here signifies property is being followed or not. Remember last time the question I discussed, the property was only two valued, 0 or 1, depending on whether 5 was in the number or not. Here the property is n valued, and depending on what the mod is, and the value, because obviously when you take mod with m, the number, the value we get in return could be anything from 0 to m minus 1. So it wasn't two valued this time, it was n valued. And of course the last last parameter is also two valued, like the example I showed you before. This again signifies whether or not our number is following the pattern that will be given inside the string. So our dp of I comma j comma k represents the length we have solved for so far, what the modulo value is, and whether or not it has been following the pattern or not. So after setting up the base conditions wherever it was required, what we're going to do is run a for loop, a simple for loop, one for all the lengths, one for all the mods, and one for both the condition. So with these three for loops, for the variables I've named here is length, modulo, and kk, are running over all possible values of this dp. And here if you look right at the end, we are adding this dp of length, modulo, and kk, same three variables जो हमने अभी तक लिए थे तीन for loops में, and we are adding it to the new dp, that is length plus 1, right? Length plus 1. These two things we'll discuss in a moment. If you look carefully, the condition that was given in the question, right, that it has to be d magic, and if the length is odd then it comes or not, and depending on whether the length is even. So that entire condition is actually being solved in just this single if line, right? If the length is odd and the new digit that we are going to put in is equal to that d magic number, and if the length is even and the new digit is not going to be d, so either of these two conditions we will make transitions. Otherwise, if condition is not satisfied, and we will just simply not make any transitions. And the simple line here that we have added is that if kk is equals to 1, or we can say if the number has been following the pattern so far, and if the new digit is more than the corresponding digit in the string that has been provided, then we simply don't do transitions. So the condition that was given in the question, and the condition that we have been discussing in every question so far about if it is not following the pattern, then we simply do not make transitions, because then we might end up getting a number that is bigger, like the number we are discussing 1 2 3 4 5 6 in the last question. If we have filled 1 2 3, then we can't put 5, right? So if the new digit is more than the corresponding digit, we simply continue. So that condition is being represented here. These above three for loops were simply for getting all the values to make the transitions, and the for loop inside that is to decide what new digit we are going to put in. So simply with this one line, we were able to solve basically this question. It's quite a simple question, and I think digit DB questions aren't that particularly hard. They're just about implementation, and a lot of them are quite similar. So I think you'll have a easier time practicing this than the bit masking questions, right? Thank you.